Hello everyone, this is Achinta Medi. So in this video I'll discuss about consecutive reaction, parallel reaction, rate determining step, steady state approximation and some problems. And if you have not watched the previous videos, links are given in the description below. So let's start this video. Now let's discuss about parallel reaction and we will determine rate constant of parallel reaction. So first of all we have to know what is parallel reaction. When in a reaction from the reactant, when reactant proceed through more than one pathway and give different products, then those type of reaction are called parallel reaction. Okay, so suppose there is a reactant A, okay, and there are two pathway, okay, and from this pathway it is giving two different product P and Q, and rate constant are different. This is K1 and this is K2. Okay, so this type of reaction are called parallel reaction. So this is the definition. When a reactant in the reaction undergoes in more than one pathway, giving rise to different products, the reaction are termed as parallel or side reaction. So in this parallel reaction, let the initial concentration of A is A initially, okay, and after time t it will be time t it will be A minus x, and the amount concentration of P and Q will be x and x. Okay, so we can write the rate of the reaction dx by dt is equal to rate of formation of P plus rate of formation of Q. Okay, so we can write rate of formation of P means dP by dt plus, and rate of formation of Q means dQ by dt. Okay, so this means dP dt means K1 A minus x, and dQ dt means K2 A minus x. That means for P, rate constant into concentration of reactant, and for Q, formation of Q, rate constant into concentration of reactant. We can write A minus x K1 plus K2. Okay, so next I will write dx A minus x and K1 plus K2 dt. On integrating I will find out K1 K2 is equal to 1 by t ln A by A minus x. So this is a first order reaction and first order parallel reaction. So it is similar to, you can see that it is like first order reaction K is equal to 1 by t ln A by A minus x. Okay, so this is the final equation. For a second order reaction, there will be two reactant molecule A plus B, and there will be different path, and it is giving product P and Q, and the first rate constant is K1 and K2. Okay, so for this second order parallel reaction, we will write the differential rate equation dx dt is equal to K1 A minus x, this is for A minus x, and for B minus x, and here it will be x and x. Okay, so it is P minus x plus for Q K2
a minus x, b minus x. Okay, next we can write a minus x, b minus x, k1 plus k2. Okay, so after integrating this equation, I will get on integrating k1 plus k2 is equal to 1 by t a minus b ln x minus a, x minus b, here it will be b and a. Okay, so this is the second order parallel direction expression for rate constant. Okay, now let's solve a problem. So for a reversible reaction where A is the reactant and P is the product, and this is for rate constant for forward direction, this is for backward direction. So here it is given that for K1 is, this is 4.0 into 10 to the minus 2, and K2 is given half of K1, half of K1. So initial concentration of A is, initial concentration is given, that means the A, as we write A here, small a, initial concentration is given. At what time the concentration of P will be 1.0 mole dm cube inverse. Okay, so for this question we have to know this equation of rate constant for a first order reversible reaction. Okay, so as we know that K1 is equal to xe by at ln xe by xe minus x. Okay, so here it is given that K1 is given, this one, 4.10 to 4 into 10 to the minus 2, and A is given, initial concentration A. Okay, and we will evaluate time t. Okay, and we don't know the xe is not given here. Okay, so we will find out, first of all we will find out xe. Okay, and next x is given, xe we will find out, and x is given here. P will be concentration of P, that means product will be 1.0, so x is given. Okay, so first of all we will find out xe. So for that we will write a p k1 k2. So from this we can write what, as it is in equilibrium state, if it is in equilibrium state we can write rate of forward reaction is equal to rate of backward reaction. So K1 A minus xe at equilibrium state, and K2, and it will be xe. Okay, so here we can write K1 by K2 is equal to xe by A minus xe. So K1 and K2 is given. K1 is this one, 4.0 into 10 to the power minus 2, and K2 is half of K1, so we can write 2.0 into 10 to the power minus 2. Okay, and here it is, xe is not given, we will find out, and A is given, A is 2.0, 2 minus xe. Okay, so from this we can evaluate xe is equal to 1.33 mole dm cube inverse. Okay, now we will put this value in this equation. So next we will directly find out t. If t will come here, K1 will come here. Okay, so I will directly write t is equal to xe a K1 ln xe by xe minus x. Okay, as it is in ln, I will write in log, so it will be 2.303 into xe means 1.33 and a is 2.0 and k1 is 4.0 into 10 to the power minus 2 log xe 1.33 minus 2. Okay, so answer will be 22.96. okay, second. Now let's discuss about kinetics of consecutive reaction. So consecutive reactions are those in which product of one reaction, if the product of one reaction will act as reactant in another reaction, then those two reaction or three reaction are called consecutive reaction. Suppose this is one reaction. If this product B act as reactant in another reaction and giving another product, so this two reaction will be called consecutive reaction. So let's assume, consider this initial concentration of A is A naught, and after time t the concentration of A, B, C become A, B and C. Okay, so we can write A initial concentration is equal to after time t A plus B plus C. Okay, and this is equation number 1. So the differential rate equation of ABC will be it will be minus dA dt is equal to as it is A in the reactant side, so I write minus. If it will be B for B, as it is in product side, so it will be positive. Okay, plus dB dt. Okay, next for this rate K1 and concentration of reactant, and next for B it will be positive as it is in the product side, so B dt is equal to, it will be K1 A, and as B is in the another reaction also in as a reactant, so it will be negative K2 B. Okay, this positive and negative signs are comes because in product side it is its amount of B is increasing, so it is positive, and amount of B in this reaction it is decreasing as it is in the reactant side, so it is negative. Okay, so for C, dC dt is equal to, it is in the reactant side, so it will be K2B. Okay, and I will numbering this 2, 3, 4. Integrating equation 2, it will give A is equal to A naught e to the power minus K1 t. Okay, next we can substitute this A value in the equation in equation 3. In this equation I will substitute this value in A. Okay, so it will be dB dt is equal to k1 a naught e to the power minus k1t minus k2b. Okay, so it will be db dt is equal to not equal to plus, I will bring this k2b here, k2b, and here till k1 a naught e to the power minus k1 t. Okay, next I will multiply exponential k2 t throughout this whole equation. Okay, so it will be db dt plus k2b exponential k2t is equal to k1 not e to the power, it will be directly, I will write k1 minus k2t. Okay, when I will multiply exponential k2t here, exponential k1t, it will be like this. Okay, next I can write, as you can see that this is like a differential equation. If you differentiate d e to the power k2t, it will give you this. So we can write d b e to the power k2t. Okay, if you differentiate the b e to the power k2t, you will get this one. And here k1 a naught e to the power minus k1 minus k2 t. So on integrating this equation, I will get, as this is as differential equation, so it will be like this. Okay, next if you, it is constant, k1 a naught is constant, so there will no any change here, so only you can integrate this part. So if you integrate this part, you will get this one. Okay, next in this step I bring this e to the power kt2 here to the right side, and it will multiply to this one and this one, and you can see that, and from this you will get this one. So this is for the product B. Product B means as we have written there, a naught is equal to a plus b plus c. So b is this one, and in the previous step we have got a naught e to the power minus k1t. Okay, in the next step we will put the value of a and b in this equation. This was the first equation, and after putting a and b value, we will get a naught is equal to a naught e to the power minus k1t plus a naught, this b value, a naught k1 k2 minus k1 e to the power minus k1t minus e to the power minus k2t, and here it is c. So c will be a naught 1 minus 1 k2 minus k1 k2 e to the power minus k1t minus k1 e to the power minus k2t. So finally we have evaluated for the variation of a, b and c, a, b and c. Okay, next I'll discuss about rate determining step of consecutive reaction. Which step is the rate determining step? So, in general, just slowest step is considered to be rate determining step. So, uh, let's consider a reaction, consecutive reaction B, and it is giving C. It is K1 and K2. Okay, so we can quantitatively we can say which will be the rate determining step. Okay, so first of all we will write the equation for C as we have already derived. So C is equal to A naught 1 minus 1 by K2 minus K1 K2 e to the power minus K1t minus K1 e to the power minus K2t. Okay, so first of all I will consider K2 is greater than K1. That means this one, this rate constant, this rate of B to C is much more higher than K1. This indicates that whatever the B amount of B in producing from A in the first step is immediately transformed to C. Okay, so we can write here as K2 is much more higher, so this value, this value e to the power minus K2t is much more smaller. Okay, e to the power minus K2t is much more smaller, so we can neglect that. In comparison to this one, this is very small, and again K in comparison to K2, K1 is very small, so we can again neglect K1. K1 is, so this is negligible, e to the power minus K2t, and this is also negligible. Okay, so the remaining part will be like this. I will write step by step 1 minus K1, and it is negligible, so I will directly write this one, K2 e to the power minus K1t. So here there is no bracket here, so K2 will, we can write here also K2. Okay, so it will be like this. K1 is negligible, so I will not write K1 here. 1 minus K2 by K2. Okay, and here it is K1t. So K2 will be cancelled out, and only 1 minus e to the power 1 minus e to the power minus K1t will be here. Okay, so this is approximate value for C. So this equation quantitatively gives us the moment B is, that says that the moment B is formed from A immediately transformed to C. Similarly, if K1 is much more higher than K2, then we can directly write A naught minus e to the power minus K2t. Okay, so you can see that when K2 is much more higher than K1. That means K1 is the first step A to B is the rate determining step. So as A to B is the rate determining step, so only rate constant of the first step is considered here. That means the value of C, concentration of C, is only depend upon the rate constant of the first step. And in this case also K2 is much more smaller than K1, so only C only depend upon the value of K2. There is no K1 here. Okay, so you can directly say that as K2 is much more smaller, so it depends upon only K2, and this is K2 is the, that means the second step is the rate determining step. Okay, now let's discuss the rate determining step of consecutive reaction in terms of graph. Okay, so this is the reaction A to B, B to C, K1 and K2. Okay, so this is the first condition where K1 is much more higher than K2. That means this part B to C is slow step and this is fast step. It is immediately converting A to B. Okay, so in this case, as A is immediately converting to B, so there is a sharp decrease in concentration of A, very sharp. Okay, but in this case K1 is small, K1 is very small, so this step is slow. So the decrease in concentration of A to B is very slow. So there is no sharp decrease. It is slowly decreases of the concentration of C. Okay. Next, in this case, as it is very fast step, so the amount forming from A to B is very slowly converting to C. So there is a high peak. But in this case, K1 is very small, so the amount obtaining from A to B, the forming A B from this step immediately converted to C. So there is a very small peak here for B. Okay, next in this case for C, this green line indicating the concentration of C. So concentration of C will increases until it reaches the final the whole amount of equal to reactant. That means whole reactant molecule part amount A, as much as the amount of A is present here, the whole part will convert it to C. So it will reaches the maximum peak, and in this case also C will reaches the maximum peak. Okay. Next, if we discuss about steady state approximation, you can see steady state approximation in this condition. So in this condition, for a period of time, after reaching a maximum peak for B, concentration of B, variation of concentration of intermediate is almost zero. That means there is no variation in concentration of B. So there will be no change in concentration, variation of concentration for a couple of time. Okay, so that portion of intermediate is, we can call it steady state zone. Mathematically is written like this: dB dt is equal to 0. So if the steady state approximation is applied, then derivative of concentration of the intermediate is set of 0. Okay, this one. Now let's solve a problem. For a first order parallel reaction, the Arrhenius factor for formation of two products are 10 to the power 10 and 10 to the power 8 second inverse, and their energy of activation. So first of all, we have to know Arrhenius equation. Arrhenius equation is what? K is equal to A e to the power minus EA by RT. Okay, so their energy of activation are 150 and 75 kilojoule mole inverse respectively. Okay, so first of all, here it is given that Arrhenius factor is given. There is a parallel reaction, and both reaction has given the Arrhenius factor. So Arrhenius factor is what? A. A is the Arrhenius factor, and activation energy is given E. EA is given. Now we know R value, and there is a condition at what temperature. We will find out temperature. Okay, temperature. The two products will be formed at the same rate. So both this parallel reaction, both have the rate of the reaction is same. Okay, parallel reaction. This is the parallel reaction. There are two products B and C. Okay, in the first case, A1 Arrhenius factor is 10 to the power 10, and in this case Arrhenius factor is 10 to the power 8, and activation energy is given 150 kilojoule mole inverse. Okay, and in this case also activation energy 75 kilojoule mole inverse. Okay, so according to the question, there is a condition that the products will be formed at the same rate. So K1 is equal to K2. K1 is for A to B, K1, and K2 is for A to C. Okay, so these two are same. So I will write this Arrhenius equation. K is equal to A e to the power minus EA by RT. So here I have written this, and next I will take log of this equation. Taking log on both sides. Okay, so first of all we will write here ln 10 to the power 10 minus, if we take ln of e, exponential e, then only this power part will remain. Okay, so that means ln, here it is a e, and it is 150 8.314 into t is equal to ln 10 to the power 8. Here this plus ln, here is a, always there is a e here. Okay, e to the power minus 75 8.314 into t. This 10 will come in front of this ln 10, and I will write ln in terms of log. So I have to write 2.303 is multiplied, and it will be log 10 plus, as it is e and it is base e, and here it is e, so only this power part will remain here. So I have to write 150 by 8 is equal to 8 plus minus 75 8.314 into t. Okay, So we can write here 2.303 into 10 to the power minus 8 is equal to 150 minus 75 into 10 to the power 3 is equal to 8.314 into t. So 2.303 into 2 is equal to 75 into 10 to the power 3, 8.314 into t. So t will be equal to 75 into 10 to the power 10 cube, 8.314 into 2.303 is equal to, and here it is 2 also, it will be 1958.5 Kelvin.
Thank you so much for watching this video. If you like it, please subscribe my channel and share with your friends.